Hello everyone and welcome to this course on analog integrated circuits. My name is Saul Rodriguez and I will be the instructor during this course. The outline for this lecture, at the beginning I'm going to talk about the course objectives, then I'm going to explain a little bit about the structured way in which we will design amplifiers. And most of the rest of the lecture I will be talking about definitions that have to be clear, so it is the common language that we should have during this course, and imperfections of amplifier of different ways of characterize them. So at the end of this course you should be able to explain how noise, signal power and bandwidth relate to amplifier performance. So we will see very soon that these three quantities are extremely important and define our design methodologies. You should be able also to use the asymptotic negative feedback model to synthesize amplifiers. So this is a very interesting design technique that you will see is very useful when you have a set of specifications. We can use this model to design amplifiers. Then you should be able to apply different techniques to minimize noise and distortion. So we will have many lectures on these aspects. You should be able to apply bandwidth optimization and frequency compensation technique using phantom zeros. So there are a few techniques around to do bandwidth optimization and to make sure that the amplifiers do not oscillate. We are going to use one that it is really advanced, that it is using phantom zeros. Compensation, we will study also typical compensation found in the literature, but we are going to focus very much on phantom zeros. Then you should be able to design current and voltage sources for DC biasing. So this is also a very interesting topic. We will see that the performance of amplifiers, it is extremely important on how we design different voltage references and current references that we put around our amplifiers to make it work. Then at some point when we have a schematic design ready, we have to implement it at the physical level. You should be able to do the analog layout of your amplifier and validate it through physical verification. Extremely important, we are going to use professional electronic design automatic tools, so you will use very modern commercial tools during the whole course. So very important part of this course is that you become familiar with modern design techniques and modern tools. And last and not least, you will do design documentation. You will write the design documentation and present your work. So what would we do that? We have seen that there is a need of have a common design methodology and procedure before you do analog integrated circuit design. It is very important you are proficient in the use of the EDA tools, and we are going to use mostly Cadence in this course, but most of the things that you learn in this course will be also useful if you use any other kind of tools. Setups, scripts are very similar, so everything that you learn in this course using Cadence you will also be applying if you use other kind of tools. Now, the most important thing in this course is that we are going to put a common design strategy. So we are going to do a structured synthesis instead of trying just to apply simulations and changes and trial and error. So we are going to use Cadence Virtuoso for the design and Spectre for simulation, and in this course offering we will use XFAB 018 micrometer CMOS technology, which you have already been used in a previous course. We're going to use a structured amplified design methodology based on the asymptotic feedback, and we are going to do sanity checks. That it is very important to make sure that every step that we do makes sense and it is correct before we continue to the next step. Extensive use of negative feedback. So in analog electronics, negative feedback is extremely important. It appears everywhere. So we are going to use extensively the negative feedback, in particular the asymptotic model. And then that will make you very familiar with details that are necessary for tape out, which is really the topic for the next course during spring. So information about the course, you will have theory and practice every day. So I will be showing the theoretical part with the presentation, but I will also open Cadence and use different setups and simulation plots to show you how it works, every theoretical part. You will implement and simulate many of these examples where, well, we will have 4 elaborations that you will have to complete, and then these elaborations are mandatory for you to pass the course. There will be also 4 homework assignments that you have to submit, and we will have a project at the end of the course that will be done by groups of 2 students, and you will present the results of your project. So very quickly, an analog design, for instance, an amplifier can contain a lot of components. It might be resistors, transistors, capacitors. At very high frequency, you will have inductors, topic of radio course, and it might look extremely overwhelming if you see all the devices that we have here. So an efficient way of designing them, it is to use a systematic way, and this is what we are going to learn in this course. So we identify in this design, for instance, we have always a source that might look something like this. You will have a load, and you will have some specifications for the amplification or the function that you want to implement. If it is an amplifier, you will have to give it some gain, and there will be some components that set the gain of this amplifier. In this particular case, it's a negative feedback amplifier. There is some passive component setting the gain, and then you will have to implement the amplifier using amplifying devices, that is transistors. So those transistors that are amplifying the signal, we will call it the signal path, and there will be these ones and these ones here. And everything else that you see around, it is called biasing. It is just generating voltages and currents that are going to place the small the signal path transistors in their right operating points. So if I draw everything else, this is a current source. These are current source and voltage references. All of these we will call it biasing. So we will split the design of our amplifier in different parts according to what I have just shown, and then we will attack the problem separately. We will design in a systematic way each of these parts. That is what this course consists of, doing the design in a systematic way. So the course has been divided in different modules. This lecture is the introductory lecture. Next lecture will be about device models and common source stages. Then we'll have theory on negative feedback, the loop gain pulse product, and this is a rather long lecture, so I will split it in 2 days. We will have a lecture on noise, a lecture on linearity, and then we will have 2 days lecture on multiple stage amplifier. At the end of the course, we will have how to implement this biasing, the current and voltage references, current sources and voltage references, and the last lecture will be on physical implementation layout. And then I will run a complete design example, so you see how all the theory on all the things that we have studied in the previous modules works. Now, when we are confronted to problem in analog circuit design, it might be the design on a filter and amplifier, really doesn't matter. That there will be many alternatives that are available, yeah, and there are different ways to attack the problem. One thing that can be done, and for instance, if you are an expert designer, is that just checking what it needs to be done, the specifications, the technology that you have, you can already pick up a good solution from the beginning. Okay, and for this you need many years of experience. You know? For the non-expert, then there are other ways of trying to solve the problem. For instance, checking textbooks, circuits in textbooks. It may be publications, checking designs that have been published in the literature, conference papers or journals. Or it might be that it is giving a reference design that needs to be modified from a previous design. So, and then that approach will be to modify or try to use what it is already been done. So typically that it is a process that will involve modification, simulation to check if it works, more modification. So it may be a work that takes a long time because it is prone to trial and error, prone to errors. No, it is trial and errors, changes. It may require many iterations, but what it is really problematic, it is that it is not sure that it will arrive to a solution. So it is uncertain a result. And sometimes it might work very quick, sometimes it will not work. So we cannot rely on trial and error and just modifying circuits that have been published. There will be cases in which they don't work, and then something new might be required. So you should be able to do that something new. What we're going to use, actually, it is what we call the reductive process based on qualitative reasoning. And in this process, what we do is to divide and win. So we will divide the problem in different chunks that we can solve separately. And each part of the problem might have different solutions. And it is in the intersection of these solutions that we can find the problem. So how we apply this reductive qualitative reasoning in analog design? Well, we have different characteristics that we have to be very clear, and it is that there are fundamental limitations on how we process information. So all signals or analog signals will carry information, and we have to understand what are the limitations. Some of the limitations are physical, some are other theoretical from information theory. Then there is just a number of analog processing functions that we can implement, and we will explain exactly what are the functions that we can do in analog, and combining these functions we can build different systems. Then we will need to apply error reduction techniques, because when we implement the analog functions, there will always be some kind of errors that are introduced. And these error reduction techniques can come from in different flavors. It might be that we can apply it directly at an overall circuit level, at the block level, or it might be that they can be applied in a holistic view as a complete system level. So I will explain a little bit more about each of these ones very soon. Then when we implement our analog functions, we will need the amplifying devices, basically transistors when we talk about integrated analog design. So we need to look for the performance and behavior of these amplifier devices. These devices, by necessity, they are nonlinear, so they will have also noise, and they will occupy space, they will have some power consumption. So there are many interesting details that we have to take into consideration for these devices. And since they are going to introduce nonlinearities and noise, we will have to apply error reduction techniques over these ones. Yeah? So these are basically the aspects that we will have to take in consideration when we do the qualitative reasoning. And then most of the course will be focused on the how to apply reductive reasoning, taking in consideration these parameters. So we start with the first one, the fundamental limitation. For information processing, we have that it is given by the Shannon's information capacity theorem. So that tells us that the information of a channel in bits per second, so we have the information channel, is proportional to the bandwidth of the channel times the logarithm base 2 of 1 plus the signal to noise ratio. So this is the signal to noise ratio. The signal to noise ratio is the power of the signal divided by the power of the noise. And here we can already see very interesting details. To start with, the power of the noise is never zero. So the power of the noise is never zero. That already tells us that we are always going to have some system that is limited by noise. The power of the signal also cannot be infinite. It is always a value that depends on the amplitude of the signal and the amount of power that we can tolerate in our system, that we can deliver to a load, the power supply, the amount of current that we have available to bias our circuit. So this is also something that is limited. And we have the bandwidth. The bandwidth of our channel, it is also limited by several reasons. One might be that our device itself are able to amplify at a particular bandwidth, but it may be also that the channel that we are using can tolerate also a specific amount of bandwidth, or it. So it is a limited resource. So all of this is going to limit the amount of information that we can pass through a channel, and then it will limit the capacity of the system. So very important, because bandwidth is something that we can relate to our circuit design. Power is also something that we can relate the amplitude of the signals, and noise is also something that we can use during design. So when we talk about the number of analog functions, there is actually not so many analog functions that we need to worry about. So let's see, the functions that we have can be amplification, that it is when we have, for instance, a signal coming from a sensor that it is very weak. It needs to be amplified to a level that can be handled by analog to digital converters, or that can be usable in another environment. So it will be needed to amplify it, and for that we need amplifiers. Okay, we need to design amplifiers. Another function that it is very common is the addition. We might need to add analog signals, or for instance a mixer for a microphone. You might need several inputs. We might need to add these signals. At high frequency we change the name of addition, we call it combiner. It's a power combiner, so we will need to do addition of radio signals coming from different paths. The implementation for combiners, it might be passive in radio design. For analog design, we use amplifiers for doing the addition. For instance, using negative feedback adders, but it can be also other kind of amplifiers. Then we have other examples. We have derivation and integration. For that, we also use amplifiers, typically negative feedback configurations with resistors and capacitors. We can implement derivation and integration. Then we have other kind of functions, for instance, selection in frequency. That is done by filters, and filters it might be implemented with passive components, but we have also a large family of filters that are active, that are implemented also using amplifiers. So we also use amplifiers here for active filtering. In the time domain, very often we use switches, or commutators. So those might be implemented with transistors, not necessarily with amplifiers. Then we have the level domain. We might need DC references. DC references or current references. Normally we need these for biasing purposes, but sometimes they are also needed in other environments. For instance, they might be used to do comparison. So it might be implemented for comparators, for the using limiters, and the DC reference typically it is obtained using band gaps reference. Band gap references. Band gap reference are implemented using amplifiers also. So we also have here inside amplifiers. Storage, typically implementations are with sample and hold. Although it is possible to do sample and hold only with transistors, very often we also have amplifiers involved in the sample and holds. And other function that we might need is nonlinear functions. For instance, multiplication in frequency for modulation, demodulation, mixers. There are ways to do in mixer in a passive way, but very often we also use active mixers in which we have also amplifier involved. So most of the analog functions we need amplifiers. So knowing how to implement amplifiers, it is a really important skill that we need to learn. So that is why this course focuses on the design of analog integrated amplifiers. So when we implement the analog functions, there is always the introduction of errors. We are using active devices, and even the passive devices, they will introduce some kind of errors, and then those errors need to be corrected. And there are different ways to do that. At the basic function level, we have a compensation technique, for instance, multiplicative or additive. So the multiplicative is, for instance, we have our amplifier here, and this amplifier might be very nonlinear. So we might need another network for doing compensation. So we will do the compensation. So we put in cascade, and then the compensation network that it is following, the amplifier will correct for this nonlinearity. So this is a multiplicative way of doing some correction. We have also the additive. The additive works like this instead. So this is multiplicative. The additive, there are different ways of representing this, but for instance, if we have a device or a system that has the following transfer function, and other has the following transfer function instead. Okay, we see that when we add these two, they will correct. They will correct, and they will result in a transfer function that it is linear. Okay, so we call it the use of complementary devices. Each one has a transfer function that is complementary to the other, so that when we add them, they correct the errors. So this is an additive technique. And then we have a feed-forward technique, and that is also pretty common. In a feed-forward technique, we have one path that we have an amplifier that introduces some error, and we have an attenuator that attenuates the error, and then we have another path that subtract this input and the attenuated version with the error, and then we have another path that adds it again here. So in this block diagram, we can see that the input, it is traveling, it is connected towards the output, and then the correction, it is done here. Okay. So we call it a feed forward technique. Yeah, also a pretty common technique. The one that we are going to study and use a lot, it is the negative feedback. So most of the time we will be using negative feedback. So we have a separate lecture on negative feedback. Then this is what we do at basic function level, but we have to take in consideration that all the blocks that we design will be embedded in a bigger system, and then many of the problems or errors that are introduced can be solved at the system level. For instance, if there is a lot of noise at very low frequencies or a lot of interference at a particular frequency, then we can change the frequency in which all our system is working by doing modulation. So we change the operating frequencies to another frequency where there is no such noise or interference. We do the signal processing there, so it is possible to do that introducing modulation. Another is that we can move the signal to the digital domain and do signal processing there instead of adding the noise or distortion that coming from analog blocks. At some point, it might be just easier to move it to the digital domain and do the signal processing there. Another interesting alternative is that at the higher level in the digital communication system, we can implement coding. So forward error correction techniques with the scrambling, for instance, allow us to correct for errors that are introduced in the analog in the blocks. So we can tolerate a large signal to lower signal to noise ratio or a larger interference if we can correct errors later. And this is typically done in digital domain. So we have we taking advantage of the benefits of high performance digital signal processing that allow us to introduce forward error correction. So that will kind of relax the kind of compensation that we need to do in the analog domain. So we have to keep in mind that this is also possible. Not necessarily we have to solve everything in the analog domain.